Hey, also in the last video we went through the concept of feed-forward neural networks. We took an input and then we propagated it all the way up to the calculation of loss. But that's only half of whatever the machine learning model does. So this feed-forward is just the 50% of the actual model which is getting trained. The remaining 50% comes in the form of backward propagation. So you have a loss value. You have to figure out like we had certain weight matrices for each of the layer. So basically what backpropagation does, it defines, or it figure out a relation between weight and the actual loss. So we tweak the weight matrices in such a way that the loss calculation can get to the can get as low as possible. Like there are certain cases where we had certain maximization problem, but for most of the neural network we use this minimization problem. This minimization problem formulated as getting the loss as low as possible. So this is the an overview of how like what we'll be doing over here. So this calculation of weights, like what we have to update, that is done by calculating the gradients meaning the slope. But for updation of the weight, there is a very famous algorithm like which we'll be using over here, which is called the gradient descent algorithm. So before starting with the backpropagation and its derivatives, we'll go through the like understanding of what the gradient descent actually is. So let's assume that this is my loss surface. This particular whole image, this is our loss surface. Now, by loss surface, I mean it's an area where I mean it's a place where the losses and the weights are actually living. It's I mean you can take it as an R3 space, and it's defined in such a way. I mean it can be anything, but it's defined in such a way for this particular case. So what's happening is you are at sitting at point here, like we have initialized, our weight matrices, like we have some random values to which we initialize those weights, and corresponding to that weight, this is our initial loss. This, you can say, this is our initial loss, whatever we are getting. Now we have to find a way such that we can propagate this loss all the way up to this bottom point. So this is the lowest possible loss which is possible for that particular given problem on which this surface is defined. Now there are few more concepts also. I mean it's not necessary that you always go up to here. You can take this path and then you can go up to here in certain cases, and then when you're training again you can go up to here in certain cases. So these are local minima, what we call them. Like these are the problems of the neural network, that it's not always certain that you will always end up into the global minima, which is like the best possible solution. You may end somewhere over here, which are good solutions, like which are good weight matrices, but they're not the optimal one. So we'll assume that we are getting over here. So how do we go over there, and why the name is gradient descent? So this is the algorithm which we call it gradient descent. Gradient meaning slope, pretty straightforward, and descent means going down. So what we do is like since we are calculating how the error, whatever the loss, error or loss, whatever we are calculating at the final point, how it is related with the weights of each of the layer, weight of layer. So if you see this particular diagram, so here we have layer 1 matrices, here we have layer 0 matrices, and here we have layer 2 matrices. So these are the only three things. I mean I'm ignoring bias for now, like the same concept applies to bias as well. So these are the only things that can be changed in order to change the loss, because loss is computed basically on the basis of these weights and biases. So how do we get certain weights and bias so that our loss can be minimized? Basically we want certain matrices which when applied the loss will give the loss for this particular, whatever the loss is coming out to be here. We want to get this particular loss because it's the minimum one possible for that particular set of problem. So for that, what we do, first of all, let's discuss why the name is called gradient descent algorithm. So let's see the algorithm first. So you have certain old weights, and on the basis of those old weights you want to calculate the new weight, so that if for the old weight your loss was here, the new weight whatever you are gonna get should bring your loss somewhere down over here. Like it should not go up. I mean, in certain cases it does goes up, then it again come back. So it might find some paths or like this. So that doesn't matter. So like the whole objective is your loss is here, and you have to define weight matrices such that you can get your loss over here. So you have this W old. What we do, we subtract eta. This is learning rate. Learning rate is basically a hyperparameter. So in this video, what we'll focus is like we'll go over a brief overview of gradient descent algorithm, and then we'll start with backpropagation derivatives. I mean, because gradient descent is pretty basics, and this for this particular video, I'm assuming that we are certain up to a level, so that we won't be needing the entire basic of whatever the algorithm is doing. It has the learning rate, and then you calculate the del W. I mean, sorry, not del W. Differentiation of error, whatever you're getting, with the old weight, and this is your new weight. So you have your old weight, you calculate what is the derivative of the error, I mean the loss, with the particular old weight, and then you subtract the old weight with it to get a new weight. Now why is there a negative sign? Why we are subtracting it? Because it is descending. Like whatever be the slope of this loss at this particular point, you have to go in a direction opposite to that particular slope, so that you get down, your loss comes down. There is an algorithm of gradient ascent as well. Now what gradient ascent is does, like we won't be covering, it's used in RL, reinforcement learning. What it does, it updates the new weights something like this, plus eta del E by del W old, something like this, not the exact derivative but something like that. But here we are adding it because that problem formalization is a bit different than what we are doing here. Here we are minimizing the error, but there our aim is to maximize the reward. This is for the sake of understanding, let's like it R. So we have to maximize reward in this particular case, so we are ascending it, but here we have to minimize the error. So this is our gradient descent algorithm, pretty basic. And then that's done. Like there are certain things which we have to consider. I mean, local minima, global minima, these are all the concepts which should be covered in like basics videos, but we will be focusing more on backpropagation and its derivative. So let's start with the backpropagation and its derivatives. So let's start backpropagation on a fresh slate, because that one got a pretty bit messy. So backpropagation, so from forward propagation, what we had, something we had weight 1, B1, we had weight 2, we had B2, and then we had weight 3, and then we had weight 3. We had a certain term loss, calculation of loss, and then now we have to calculate the derivative of loss with respect to W1, derivative of loss with respect to W2, derivative of loss with respect to W3. So for now we'll focus on W3 only, and then after that everything is pretty simple when you consider it in a matrix form. Pretty simple. The only differentiation is this one, which gets pretty tricky. Let's start with it. First, let's see the flow, how it went from input to calculation of loss. So we had certain x, then here comes your W1, and then here comes your B1. After this you get your Z1. Let's just erase this. Then on Z1 we apply an activation function to get activation value of the first layer. Then again from here we had W2, we had B2 to get Z2. Again we apply some activation function, and we have discussed that this function could be the same as this one or it could be different, but for the sake of simplicity we are taking both to be tan h, same function, to get A2. Then again here you have your coming in W3 comma B3, again linear transformation, you will get Z3. Then on Z3 we'll apply softmax. Softmax will give us S3, and then from S3 we'll calculate our loss, which is basically the formulation of loss is this minus summation I is equal to 1 till 10. For our case we are considering 10 classes, like it could be any general value, k is equal to 10 or I is equal to 10. yi log of si. So si is coming from here, and then y, these are the actual label. And remember, these are all, y is a one hot encoded vector. So basically, if your class value is 1, I mean if in your image it's written 1, so it will be something like this: 0 1, then rest all 0, and this will be 10 cross 1 for our particular case. So this is pretty much our flow. Let's write it. Loss we are calculating this, where if you see, what is your si is basically e raised power zi divided by summation I is equal to 1 till 10 e raised power zi. So this is your si, softmax probability. Basic, simple. So till now we have covered what we have done in forward propagation. Now let's go through how we have to calculate the the loss functions. Okay, so if you see, let's first focus on this particular term, log of si. Let's calculate its differentiation with zj. Z is this particular value and si. So you see there is a direct relationship between both these two, so we can use derivatives. Now, what is si? Si is something a function of e raised power something, or typical formulation. So what we can do, its derivative we can write as something like this. We can write like this using chain rule: del of log si with respect to si into del of si with respect to del of gj. Cool. So this will what? This will be log of si with respect to 1 upon si into del of si with respect to del of gj. It's just to make things a bit simpler. Now let's focus on this particular thing: del of si with respect to del of gz. Del of si with respect to del of gz. Now si, if I will write, it is what? It is basically e raised power zi divided by summation I is equal to 1 till 10 e raised power z. Let's write it j. We have to calculate its derivative with respect to del of gz. Now what you can do, okay, rather than using si, let's use log of si. We have to calculate differentiation of this with respect to this. Log will make this a bit simpler and nicer. So if you apply log by using the logarithmic rule, what it will become? It will simply become like log of si will become this particular term. Let me erase this. So I'm trying this out like for the first time only, so I'll also fumble a bit. So that's pretty much okay. So log of si is if you calculate log of si, it's basically log of e raised power zi minus log of summation I is equal to 1 till 10 e raised power zi. Cool. This is the log of si. Now we have to calculate the derivative of this with respect to gz. Now we can separate it out, so it becomes del of log of e raised power zi divided by del of gz minus log of summation I is equal to 1 till 10 e raised power zi divided by del of gz. Now if you consider this, so what it will become? Again, log of e raised power zi is basically simply zi. So this is basically log differentiation of zi with respect to differentiation of gj, and this term we'll figure it out a bit later. Let's write it as it is: I is equal to 1 till 10 zi divided by log of gj. Now if you see this, if I is exact is equal to j, if I equal to j, then this will become 1. Otherwise it will become, if I is not equal to j, it will become 0, because z won't depend on it. Zi won't depend on zj unless I is not equal to I is equal to j. So you can write it like as an indicator random variable. So it can be written as sorry, not random variable, as an indicator variable. Indicator variable will be something like 1 if I is exact is equal to j. So this is the notation how we write it. If it is not, it becomes 0. Pretty simple. So this term we are sorted out. This term is done. Now we are focusing on this term. So this term is basically what? Log of summation I is equal to 1 till 10. This is also pretty simple. Just to explain, I have to write it. This is e raised power z. Sorry, e raised power zi. e raised power z I divided by del of zz. uh, Now what happens if you expand it out, right? So all the other terms except from z will turn out to be 0. So the only term which will remain over here is basically log of e raised power cj divided by del of zj, because if you see if you expand it out, so if I is not equal to j, whatever it will be, it if you take a log and then differentiate it, because basically if I is not equal to j, this term becomes constant, and derivative of constant with any random with any variable, it's turned out to be 0. So from summation only this term will remain, and this is basically gj. Cool. So it is gj only. mm, or am I missing something? uh, So how it goes? Let me think about it once more. E raised power gz t t t t t t t t t t t t. So yeah, let's see how it goes. So it shouldn't be something like this. Maybe okay. So it becomes gz. So what's our final derivative? Final derivative is del of log si. So your del of log of si with respect to gz turns out to be something 1 if I is exact is equal to j minus zj. Okay, but log of e is let me think once more. It is derivative of log of all these, right? Oh, sorry, not like that. Yeah, my bad. It is derivative of log, right? So you have to consider this term as a some let's consider it as an x. So it's basically del of log of x and some function of dz. So you have to again apply chain rule over here. So you have to define with something like this into del x by del zz. So this will turn out to be 1 by x. So it's basically what's coming out to be this particular term. This particular term will come out to be 1 upon summation e raised power zi, I is equal to 1 till 10, and then differentiation of again x the same term. So it will be differentiation of summation I is equal to 1 till 10 e raised power zi divided by. Now there is a direct correlation. It was differentiation of the logarithmic. So first you have to sum it all, and then you have to take out the log, and then you have to differentiate it. So you can't directly apply it over there. So that was my mistake, and that I figured it out because you are differentiating with respect to zz, and then again a zz term was coming over there. So that was something wrong going over there. So yeah, so makes sense now. So this is basically what this is basically 1 upon summation I is equal to 1 to 10 e raised power zi, and then now here you can say that zz, sorry, this is differentiation with zz. Now here you can say that only the zz e raised power zz terms will remain. So this will becomes to be e raised power zz, because e raised power z1 plus e raised power z2 up to e raised power z10 divided by, if you differentiate it with respect to e raised power z2, let's say. So these term will come out to be 0, these all terms will come out to be 0, and then it will be differentiation of e raised power z2 with respect to e raised power z2, which is again e raised power z2. E raised power x differentiation with x is e raised power x. So this comes out to be this one, and then it could be written as something like this, e raised power zj. So this is what this is basically sj. Clear? So now if we see this entire term, so del of log of si, simple, del of log of si with respect to zj turns out to be 1 I exact is equal to j minus sj. Cool. Now this is what one conclusion we have came over. Now what we had to calculate was where is the loss? Yeah, we had to calculate the loss differentiation, right? So we had to calculate del of L with respect to del of Gz. We are considering a particular J over here, and then we can consider the entire matrix. I mean, this is particularly a vector of 10 plus 1. I mean, we are considering only one element, and we are seeing what's the effect of this particular element with the respect of total loss. So the entire vector could be calculated in same way. I mean, we can after calculating one element, we can simply formulate it for the entire vector. So your loss was something like this: minus summation I is equal to 1 till 10 yi log of si. Cool. And then we have to differentiate this entire thing with zz. Cool. Now here see yi is a constant variable, like it's not depending on zz because it's the actual value. So if we take the derivative inside, so this will simply turn out to be minus summation I is equal to 1 till 10 yi derivative of log of si with respect to derivative, like this is entire, I mean you can't just exclude it out, derivative of zz, right? Now we know what this particular thing is, derivative of log of si with respect to derivative of zz. It is 1, so this simply becomes this summation I is equal to 1 till 10 yi, and then this will become your 1 if I is equal to j minus s j. Cool. This is why we were taking the si log and then we are calculating the derivative to make the things easier when we are doing with respect to the loss function. Now again I is equal to 1 till 10. Now what happens is, if I is exact is equal to j, it becomes 1, otherwise for all the, here is a minus sign, here is a minus sign. So we can, it becomes basically yi sj minus yi 1 if I is equal to j. Cool. I took the minus sign inside. So now if I separate it out, and then for example let's see this particular term. So if I is equal to j, it becomes 1, otherwise it becomes 0. So 0 we are not considering, I mean it doesn't make any difference if it becomes 0 also. So we are considering I is equal to j, because for any other cases it doesn't make any difference. So we are considering this special case I is equal to j. When I is equal to j, this will become what? Yj, and this will become 1. So this will come out to be summation I is equal to 1 till 10 yi sj minus, these are all in summation, minus yj. Now you can just took the summation outside. Summation I is equal to 1 till 10 yi sj minus summation I is equal to 1 till 10 yj. Okay. Now did I miss something? I don't think so. Yeah. Now here is j and here is yi. So j you can take it out, sj will come out, and then I is equal to 1 till 10 yi minus I think I missed out something. I think I missed out something over here. So yi I is equal to j. Okay, so here there won't be any summation, right? Why here there won't be? Because for all the other cases, if I is not equal to j in the summation, it will turn out to be 0. So only the term remains is yi, and then it will become 1. So this will remain only yi. So there will not be summation, and this will be yi. Yi you can write, or yj you can write. For the sake of simplicity, I mean to make things look good, we can write yj, because I is equal to j. For that only this particular term is remaining. Now summation of yi from I is equal to 10, this turns out to be 1 because we have one not encoded vector. So this simply become sj minus yj. So pretty simple, pretty neat forward. So we have del L by del of z j turns out to be sj minus yj. Now you can turn you can write it in a vector form, I mean in matrix form. What you can write it like del L by del Z. Del Z is now your entire vector. It can be S vector minus Y vector. Simple. Now where were we? In this particular we were here L, and then we came out all the way back up to Z. Yeah, so we were at L, we came back all the way up to Z. Now we have calculated Z, we need to update W. So how Z and W are related? So if you see, Z3 is basically what? Z3 is basically uh, A2, right? Yeah, A2 into W3 plus B3 or something like this. W3 transpose A2 plus B3. Now I'm writing it in a matrix form, it doesn't matter. Yeah, sorry for the disturbance. Like, let's continue where we left off. So Z3 W3 transpose A2 plus B3. This is how our Z3 look like. So we have to differentiate this Z3. We have to differentiate basically what? So I can write this like this, right? ZL by del of ZZ is equal to sorry. Let's we had to at the end of the day calculate this, right? So we can write it del L by del of ZZ into del of Z. Let's remove ZZ for now. Let's consider it in vector form. Del of Z by del of W3. Simple chain rule. We know this. This is what? This is basically S minus Y. And now we have to differentiate Z with respect. We have to differentiate Z with respect to W3. So it will come out to be A. Right, B becomes constant, it goes out to be 0. This we are differentiating with, so the only thing remains is A. So at the end of the day, del L by del of W3 turns out to be S minus Y into A. This is A2, activation function of second pair, activation value of second pair. So pretty much it. Now that's done. That's all we have to do till now. After that, whatever we will be differentiating, so we came up to here Z, and then we differentiated it with W. Now if we have to differentiate with W2, there will be again like we have to follow this path, and then we have to go up to here. So let's do it for like one of the layer for W2, and then we can simply move forward for to code all these things, all these derivatives into our system. So we have del L by, now we have to calculate this thing. Now we are done with this part. We are done with del L by del W3. So we have to remove this. We don't need it. Now we have to calculate del L by del W2. Again, we have to come back up to that point using the same thing. This I can write del L by del of Z3 into del of Z3 by del of W2. Simple. Now we are done with this, we know what it is. Now we have to differentiate del of Z3 with respect to del of W2. So to go up to there, what we have to do, we have to differentiate del of Z3 with respect to A2, and then A2 with respect to Z2, and then Z2 with respect to W2. So the chain rule, what I can write like this is del of Z3 with respect to A2, and then A2 A2 with respect to Z2, and then Z2 with respect to W2. A2 with respect to Z2, and then Z2 with respect to W2. Let's see how Z3 and A2 is represented. So Z3, what basically Z3 is? Z3 is W3 A2 plus B3. So if you differentiate it with respect to A2, what you'll get? You'll get simply W3. So these terms come out to be W3. Now how A2 and Z2 is related? So A2 is basically f of Z2. Cool. So if you differentiate A2 with respect to Z2, what you'll get? You will get f prime Z2, where f is the activation function, and we have already calculated out what's the derivative of tan h activation function looks like. So f prime Z2. So this turns out to be f prime z2. And then if you see what z2 and w2 are related, so z2 is what? Basically z2 is w2 a1 plus b2. So if you differentiate z2 with respect to what? With respect to w2, you'll simply turn out to be a1. a1. So what this become? This become s minus y and then a. I mean, we know this del L by del Z3 is basically S minus Y into A. No, sorry. Del L, this is not A. A won't come here. So this becomes S minus Y. Del L by del Z is basically S minus Y. So this will become S minus Y multiplied by W3 multiplied by F prime Z2 multiplied by A1. So this is how del L by del W2 looks like. So pretty simple, and then you can go one step more backward. You'll get again one derivative of this activation function, and then you will reach simply W1 also. So this is how we get all the weights derivative. Now once you have those derivatives, you have del L by del W1, del L by del W2, and then you have del L by del W3. Now all we have to do is like we have to update the weight. So our new weights will become gradient descent algorithm. Whatever old weight let's consider for W3 only. W3 new will become W3 old minus eta del L by del W3 old. Simple. And then again you will have certain weight, then again you will compute derivative, again you will update the weight, again you will compute the you have updated this weight, again you will do the forward propagation, you will get some loss new, again you will compute the derivative, again you will tweak the weights, then again forward process, then again same process, same cycle goes on until we reach a certain desired loss volume, loss value, or maybe you end up being iterating for a certain number of epochs and you are satisfied that yeah, whatever loss I'm getting after this particular epoch, this particular iteration is sufficient enough for my problem to be solved. I'm getting pretty good accuracy. That's what it means. Now what for the coding part, what we'll do, we won't be using anything of batch because batch makes a bit trickier. All I want to show is like how we can code the derivatives, and then we can simply do this particular repetitions, and then we can get our own neural nets. So what we'll be having one sample, like one sample I will do forward pass with it, like let's say this is x, this is my x1. I will do forward pass with it, I will get certain loss, I will update the value, I will do backward prop, simply x2 x3, and then I'll keep on repeating for all these x for a certain number of epoch, and then I'll like iterate over epoch also. So there will be two for loop, one for epoch and then one for iterating over the entire sample. So batch size is basically one in this case, but yeah, we can do in batches also, so that's not a big deal. But yeah, let's go to the coding part of this, and then we'll continue with the same point where we left in the forward propagation, and then we'll see how well we can do in the code over there. Yeah, see you in the code.